Today, let's deal with the moment distribution method using the continuous beam with sinking support. You can see the beam with the sinking support there. So, as you know, in the analysis of fixed beams, the right hand side support settle. The right hand side support. Right hand side support settles down. The fixed end moments are produced by the 6CI delta by L1 square. As you know, it was produced by the 6 when the right hand side support settles down. So, similarly, the fixed end moments produced are given by the equation, as you know, 6CI by delta, which will be anti-clockwise, where delta, as where we can say delta is the settlement, I is the flexural rigidity, and L is the span of the we can say L is the span of the fixed beam. So similarly, if the right hand side support yields, the fixed end development will be 6CI by delta by L2 square. So in you can see this figure, and you can say that in moment distribution with the fixed end moment due to settlement of support are added to fixed end moments due to the loadings, you can say. And this is the you have to take the conditions of these this, and you have to solve the conditions with sinking support, and rest all the procedure will be same in the moment distribution. So if you consider I given a one problem here. If support this is the continuous with support B yields by 9 mm, with support B yields by 9 mm, that is the delta value, and here they had given the value of of 1 into 10 raised to 12. You can say you can consider this continuous beam. So first procedure, first step, as you know, it will be same, but here it yields by 9 mm, then delta is given the value and the A is given the value. So you can calculate the fixed end moment according to the loadings. So we have the fixed end moments, that is we already have this loading with unequal distance minus WAB square by L square. As it is the support yields by 9 mm, we can say minus of 6CI by, because it is anti-clockwise, you can say it is minus of 6CI by delta by L square. So we have to substitute the values, as you know, W is 60, and you know the values, anyhow we can place these values and substitute the values. You know, 6CI they had given the EI value, and 6CI 1000 it will be, and 1 they are given in mm. I converted into meter and substituted the value. I'll get the value of 19 minus of 9, as it is in clockwise, anti-clockwise it will be in minus, and minus of 19.33. Similarly, MFBA you have to calculate same thing using the formula WAB square by L square. So you will get the, by substituting the values, you will get with 20.67 kilonewton meter. Same thing MFBC you can calculate. We have MFBC here. So as it is in a clockwise, MFBC is in, you can say it will be in clockwise direction. So I didn't mark it here. Okay, as it will be in clockwise direction, you can use the formula plus CI by delta L square by L square. So you will get the 58.5 kilonewton meter. Same thing with BC and CB. Here minus, it will be plus here. So here the MF you can say here A, B, C and D. So you have the MFCD. We have, as it is a cantilever moment here, because as it is a cantilever moment here, so it will be in minus of 20 into distance we have 1 meter into 1 is equal to 20 kilonewton meter. As usual, we have to calculate the distribution factor values. Joint member, how many members are there you have to take, and how many B and C are 2 joints, but to see towards it's not going, C towards D will be 0 here. Sorry, C towards D will be 0. C towards D will be 0. If you have to substitute the value, when, as you know, distribution factor is K divided by sigma K, we have to distribute we have to substitute the value. You should remember that when we add these two terms, it should be equal to 1. So this is equal to 1 and this is equal to 1. Whatever we are solving the method is right. So after this time, we have to calculate for a moment distribution table. I just taken a simple problem to show you. As usual, using the moment distribution table, we have to solve as using the moment distribution problem. We have to solve this moment distribution table with the distribution factors, and these are the fixed moments. These are the fixed members. We got the values, and as you know, balancing and carry over. So this is minus 61.4 minus 20. We are going to minus 40.5. Carry over it to both. Carry over it, as it is both the ends are fixed. There is no need to balance. Carry over. So whatever the value it is coming, just minus 58.5 minus 20.75 it is going to come, and this into make it this one. So we are going to values of multiply this, what are the values it is coming from this, multiply the value with these two terms. You are going to get minus 19.3, 21.29 and 1.9663, whatever the value. As you know, free movement, for free movement diagram in AB, as you know, the free movement diagram in AB is a triangle. As you know, AB is a triangle in the problem with maximum ordinate under loads, and its the value is given by AB. So WAB by L. Similarly with BC, the symmetrical, it is a symmetrical parabola, and the maximum ordinate is given WL square by 8. So we got the 40 kilonewton, 90 kilonewton meter. So this is the bending moment diagram I plotted using these two values, and using these values 1.96 and 63.25 and 90 and 90 we got here, and 20 we got here. This is the value. Using the values I got the free body. Using the positive values I plotted the and negative values I plotted the free body bending moment diagram of the continuous beam. So thanks for watching.